You know, we all see the giant power plants, right? And those endless lines of transmission towers stretching over the horizon. But what if I told you the most critical part of our entire power grid is something most of us have never even heard of? Today, we're going to pull back the curtain on busbar protection, the invisible system that stops catastrophic blackouts before they can even start. So let me just ask you this. What do you think is the single most critical intersection in our entire power grid? I mean, the one spot where a single failure could cause the absolute worst, most widespread disruption? It's not what you think. It's not a power plant or some massive tower.
It's called a busbar, and honestly, the best way to picture it is as Grand Central Station, but for electricity. It's this central hub where power from generators, transformers, you name it, all merges together before being sent out on all the different power lines. It is the ultimate electrical crossroads.
But just like any major transportation hub, a disaster right there at the center, it can bring everything to a grinding halt. So what happens when something goes horribly wrong at this one critical intersection?
Well, that disaster has a name. It's called a bus fault. This isn't just any old short circuit happening on a line miles away. No, this is a short circuit happening directly on the bus bar itself. It's a failure right at the very heart of the substation, which is the absolute worst place for it to happen.
And yeah, the consequences? They're huge. A bus fault unleashes so much energy it can cause catastrophic damage to equipment. It can trigger massive, widespread power outages because you've just taken out a key junction point. And it can throw the entire grid into chaos, causing major instability. So protecting this one piece of equipment is absolutely vital.
Now here's what's really interesting. The whole philosophy behind protecting the grid. The goal isn't to build a system that can never ever fail. I mean, that would be impossible, not to mention insanely expensive. Instead, is this quote from our source material explains, the real goal is to accept that, hey, failures will happen. The profitable and smart thing to do is build a system that can intelligently deal with the effects and limit the damage. And that, right there, brings us to the heroes of our story. The systems that aren't designed to prevent the failure, but to contain it in the blink of an eye. These are the guardians of the grid, protective relays.
Now, you might be thinking of the simple little fuse in your house. But a protective relay system? Oh, it's on a whole other level. A fuse is, well, it's dumb. It just melts when the current gets too high. A relay is intelligent. It's constantly sensing and analyzing current, voltage, all of it. A fuse is a one-and-done deal, while a relay is resettable. And the most important part? A fuse is slow. A relay system operates in milliseconds.
So here's how it all goes down. First, a fault happens on the busbar. Second, the protective relays instantly, and I mean instantly, detect that something is wrong with the current flow. Third, they blast out a trip signal to all the circuit breakers connected to that bus. And finally, bam, those breakers fly open, completely disconnecting and isolating the faulty bus from the rest of the grid.
And get this, all of that, it happens in less than 1/10 of a second. That is literally faster than you can blink your eye. The system detects the problem, makes a decision, and acts before the catastrophic damage can really even get started. It's incredible.
So how in the world does the relay system make such a huge decision so incredibly fast? Well, it all comes down to a really simple, almost beautiful idea. Let's call it the perfect balance principle.
The technical name for this is differential protection, and it's brilliant. Basically, you create a protective zone around the busbar. The relays then live by one simple rule. What goes in must come out. The total amount of current entering that zone has to equal the total amount of current leaving it. Simple as that.
Okay, let's walk through this. Scenario 1. Imagine a fault happens on a power line way outside the busbar zone. A ton of current is going to flow in through the bus, but then it's going to flow right back out towards that fault. So the total in equals the total out. The relays see perfect balance, they correctly figure out the problem is somewhere else, and they do absolutely nothing. They stand down.
But now, look at this. A fault happens inside the zone, right on the busbar itself. Now current comes rushing in from all the connected lines, all feeding that short circuit. But almost nothing is flowing out. What goes in does not come out. The relays see this huge, undeniable imbalance, and in milliseconds, they give the command, instant shutdown, trip everything.
It seems so simple, right? But of course, there's a tricky complication that makes these systems even more impressive. They have to be smarter than the surge itself.
So this brings up a really critical question. What happens if a massive fault outside the zone is so powerful that it temporarily blinds the sensors that are measuring the current? Could the whole system get tricked into shutting down when it shouldn't?
Well, this challenge is called current transformer saturation, or CT saturation. Think of it like this. That massive external surge is like a deafening noise that completely overwhelms the sensors. For a split second, they just can't report the current accurately, and they might accidentally hear an imbalance that isn't really there. And this could fool the relay into causing a huge, unnecessary shutdown.
But this is where the engineering gets so clever. Modern relays don't just measure the amount of current, their algorithms actually analyze the shape of the current's waveform. They're smart enough to recognize the distorted, messy signature of a saturated sensor versus the clear, unique signature of a true internal fault. Basically, they can see right through the blindness.
So there you have it. Deep inside our electrical substations, these silent guardians are on watch, 24/7, balancing the flow of power. They operate in milliseconds, making these huge decisions that prevent catastrophic failures and, keep our lights on. It really makes you wonder, what other invisible, lightning-fast systems are out there quietly keeping our whole world running?